Okay, my first question to you is just going to be, and we can just answer, like shout out your answers or volunteer your answers. When I say the word inequality, what do you think about? Zachary?
Greater than or less than signs.
Greater than and less than signs. Greater than, less than, even greater than or equal to, less than or equal to, right? Jacob or Mitchell, what are you guys giggling about?
America. Oh.
I didn't even hear what he said that time.
America. What do you think when you think of inequality?
Oh, that is kind of funny. Oh, you think about Pac-Man, so maybe how your teacher, Pac-Man, crocodiles, alligators, those types of things. What else happens when you have greater than, less than, greater than or equal to, less than or equal to? What do you have to be thinking about in your head when you see those things? Oh, Blake? Oh, multiple solutions. So usually, like, if it's an equal sign, you could have multiple solutions, but there's like a set number of solutions. Like in our warm-up, we had 5 solutions. That was it. If you have an inequality, you have multiple or maybe like infinitely many solutions a lot of times. There's a whole section that counts for the inequality. What else do you think of? What if I clarify and I talk about graphing inequalities? What do you have to think of when you graph inequalities? There has to be some kind of shading. Very good. Anything else? Just trying to picture those in your mind, Ethan. Close his eyes for a little bit. Thinking of the inequality. Someone else had their hand up. No? I dreamed it? Close my eyes. What's the big difference in graphing inequalities if you have less than or you have less than or equal to?
An open circle.
Zachary?
Dotted line or a solid line?
Dotted line versus solid lines. And then, David, you were saying?
Open or closed.
Open or closed. Now, those two are kind of separate depending on like what type of inequality you're actually talking about. Back in Algebra 2, you guys did quadratic inequalities where you graphed a parabola and then you had to decide, like, is my parabola solid or dashed? Do I shade inside my parabola or outside my parabola? So that would be more along the line of what Zachary gave us for dotted versus solid lines. And then probably going back to Algebra 1, which is sort of more of the feel of what our answers are going to be on a number line. If you don't have like a coordinate plane, 2 dimensions, you just have the 1-dimension number line, then you just have to decide, like, should my dot be solid? Or sorry, should my dot be closed or open? Should I shade to the right or the left? Should I shade in between? Should I shade outside? Right? Those are the kinds of things that you ask yourself on a number line, which we're going to do today. The only difference for today, we're going to be working under this idea of open, closed, and shading on a number line. Instead of using open and closed circles, we're going to switch to what we use for interval notation. So think about interval notation. If we want to exclude something in interval notation, we use parentheses. So we'll use a parentheses on the number line in place of the open circle. Okay? And then if we want to include something in interval notation, we use a bracket. So instead of drawing a closed circle, we'll draw a bracket right there. So it will follow very closely to what you have written down in interval notation. Now here's where I'm going to need you to talk with the people around you, and I know we're in our seating arrangement for a test for geometry. So feel free to get up out of your seats or move closer so that you can hear and talk to each other. If I give you this function, f of x equals x squared minus 5x plus 4, and I ask the question, when is f of x greater than 0? Okay. I want you to write your answer in interval notation. So the main question you're asking in your small group is, when is f of x greater than 0? And so to have that conversation with your group, you might need to clarify a few things. Some questions that I think might need to be clarified for some of us is, what the heck does that mean? if Ms. Cronky wants to know when is f of x greater than 0, what does that mean? And even possibly using your calculators or your Desmos apps, those types of things, what does that look like on a graph when f of x is greater than 0? How could I see that visually on a graph and know then that f of x is greater than 0? Okay. So you want to have those conversations. When you're writing it in interval notations, okay, you are writing the interval notation for the x values that make f of x greater than 0. So you only have one set of numbers that you're going to work with an interval notation. I'm going to go investigate that here in just a second. Okay, so write that in interval notation, and as you finish your discussion, you can also sort of answer this question: what were the key numbers within your group to help you decide your answer? So I'd like you to have a discussion. Be willing to share their interval notation answer. Emily?
We said from parenthesis negative infinity, comma 1, parenthesis, in union with parenthesis 4, comma infinity, parenthesis.
Were you close to that? Did you have that? Not at all? You had brackets. Where? Everywhere? Okay, Mitchell, you want to convince us why we should have brackets?
That's kind of where it stopped before it was 0.
That's where it stopped before it hit 0.
I'm not sure this is my bad.
Wait, he's convinced himself something else.
My bad.
He says, my bad. What happens at 4 and 1?
It hits 0.
It is the 0.
So it has to be greater.
So let me answer the question. What were the key numbers in the interval notation? Your zeros, right? Your zeros were really important because what happens at the zeros? F of x is actually equal to 0. And then if we have odd multiplicity at those zeros, that we know through odd multiplicity we're actually going to cross the axis, which would mean we're crossing from positive to negative or negative to positive, right? Okay, so we're actually changing the sign of our value once we hit that 0. So Mitchell has just realized that those were the zeros. They were actually equal to 0 there. Correct, Mitchell? And you're now on board with us. Okay. So 1 and 4 are really the key numbers, and that would be true for any polynomial. We want to find those zeros, those x-intercepts, and we want to use those as the boundaries for our interval notation, because they're going to cut off positives and negatives for us. Okay? So here are some things that you should write down in your notes. Solving polynomial inequalities. One thing I didn't put up here, but we should make note of. One side should be 0, maybe I'll say. I can't say set equal to 0. So you're going to have, instead of an equal sign, you're going to have greater than, less than, greater than or equal to, less than or equal to, and you want the other side to be 0. Less than 0, greater than 0, and those types of things. Key numbers are your zeros. So this goes back to section 2.5. We spent a lot of time finding zeros of polynomials. We're going to find the zeros of the polynomial in the inequality. Okay. Step 2. Some way you have to be able to test the intervals for positive and negative. When I was going around to different groups, I stopped at the group up front here, and Nick had a conversation with his group about why he thought one of the numbers should be 5, because when you plugged it in, it worked. It was positive. So I use Nick's method when I'm testing intervals. I choose numbers in between my key numbers, I plug them in, and then I just figure out if my y value would be a positive or a negative, and I mark that whole interval. Because it will, the rest of the interval will have that same sign until it hits the other 0. Okay, so you can just check a random x value in an interval, and that'll test for positive and negative f of x. Your answers should look like interval notation, so I'm going to want to see that interval notation that Emily gave us for their group. I'm also going to want to see a graph on a number line, and that should follow pretty simply from your interval notation. This would be the piece where there is some shading. There's that idea of the open or closed circle, but we're going to replace open and closed circles with parentheses and brackets. So we're just going to use the same things that we use in interval notation. And you'll see this in our first example, how that looks. I'll write it. Now, when I do my work for these, I know that my answer has to have an interval notation. It also has to have a number line graph. So that's part of my answer. I have a second number line graph that I use for all my work. So, there's some work that I can show algebraically, and then I draw this number line that will not be my number line answer, but it will be part of me thinking through the process. So you're going to see me draw two number lines, one for my work, one for my answer. Okay. So here's an example of what you're going to see on a homework assignment. I didn't finish changing this, so don't write it down. It didn't save. I think I want to get to there. Oh yeah, this is what I want. X cubed minus 3x squared minus x is greater than negative 3. Okay, so first of all, remember I said one side should be set equal to 0, so we're going to add 3 to both sides. Okay, we want one side of the inequality to be 0, so add 3. That will give me x cubed minus 3x squared minus x plus 3 is greater than 0. We want to find zeros, right? Because those are our key numbers. So my question to you is, how can you find the zeros of this polynomial? Blake? Factor by grouping. So if I were going to find the zeros for this, I would use factor by grouping. X cubed minus 3x squared, I group the first two terms together. Then I group the last two terms together, negative x plus 3. This is not multiplication. I'm not doing any distribution or foiling. I'm simply just grouping them. And right now, I look at only the first two terms. So I'm ignoring this x, negative x plus 3. What can I take out of x cubed minus 3x squared? X squared. And when I take or factor out x squared from both of those, I'm left with x minus 3 in parentheses. Okay, so that's my first group. Now I ignore my first group and I look only on the second group, that negative x plus 3. What could I take out of two terms, negative x plus 3? A negative 1. If you can't take anything out, like you don't even have a negative in front of the first thing, you take out a positive 1, a plus 1. Okay, so you always have to take out a sign right here. It needs to say like minus a number or plus a number. We can take out a negative 1, which when I divide each of these by negative 1, they're going to change signs. So it's now going to be positive x minus 3. I've said this a couple of times, but I'm going to say this again for factor by grouping. If these parentheses don't match, you can't factor by grouping. You can't list out 4 different factors. These have to match in order for factor by grouping to work.
Why did you change it to equal 0?
Because I'm finding the zeros. So when you're finding zeros, you're finding places where it does actually equal 0. Okay. Since these two parentheses match, I can undistribute them or factor out the x minus 3 factor. And my other factor is formed by these sort of coefficients, x squared minus 1. And then at this point, you really could solve that x squared minus 1 factor by reverse PEMDAS. If you think back to the warm-up where Raven gave us the x plus 4, x minus 4 for our difference of perfect squares, this could also be x minus 3, x plus 1, x minus 1, because that's a difference of perfect squares. And so what are my zeros?
Plus or minus 1 and 3.
Plus or minus 1 and 3. Okay. Now, you have found the key numbers. This is the number line where I do all my work. Okay, so this is not the number line of my answer. This is the number line of my thought process. I'm going to draw out a number line, and in order from left to right, I'm going to put my key numbers. So my key numbers were these zeros right here. I'm going to plot them on my number line. -1, 1, 3. And what I want to do in each of those intervals, now my number line is broken up into 4 sections. Left of -1, in between, right of 3. And I want to figure out, in those 4 intervals, will my graph end up being positive or negative? In order to do that, we're going to use that method I was talking about with Nick. We're just going to pick numbers and plug them in and see what works. Okay? So one of my favorite numbers to always plug in if it's not a 0 is 0. So 0 would be over here. If you plug 0 into this original polynomial for all those x's, is your answer a positive or a negative f of x?
Wait, don't you have to go to the one above?
No. You use the one where you have set it equal to 0 inside. So if we plug f of 0 in, then we get positive 3. We know this whole section in between -1 and 1 is positive. Okay, so that's me marking that. Now, I want to just check, and you should do this on a quiz or a test, check the other sections, right? So now, a good number to pick between 1 and 3 is 2. So I would calculate or evaluate f of 2. That'll be 2 cubed is 8, minus 3 times 4, that's -12, so -4. Minus 2 is -6, plus 3 is negative, right? So at this point, I don't even care what the number was. I knew it was going to be negative. When I do those intervals on the far ends, I usually pick kind of big numbers, because if you're working with a polynomial, you'll be able to tell without doing much calculation if that's going to come out to a positive or a negative. So like if I'm testing numbers that are greater than 3, I might pick 10. Okay, and when I plug 10 in over here, f of 10, that's 1,000 minus 300 minus 10 plus 3. I can tell that's still going to be positive, right? So on those far ends, if you pick larger numbers, it just exaggerates those exponents, and you can tell quicker without much calculation if it's going to be positive or negative. I can do the same thing on the other side. I might pick a -10, so f of -10, this is going to be -1,000. Adding and subtracting this little chunk of stuff right here isn't going to make a difference, so it's going to be negative. Now, also using what you know about like multiplicities for those zeros, we found 3 zeros, 3, 1, -1, and they all had multiplicity of 1. So we knew at each of those zeros we were crossing from positive to negative. So we could have also said, like, once we identified that very first one, f of 0 is 3, we knew that our polynomial was positive there. So when we got to the next 0, we would switch, and we would switch, and we'd be negative. So you can also use knowledge about what's happening with the graph without even seeing the graph to know if it's going to be positive or negative. Use that on a quiz or a test. I'd also say check some of those f of different numbers so that you can verify if they're actually positive or negative. If you had even multiplicity, you could have a positive next to a positive interval. So you have to be aware of that. Okay, so remember, that number line is not my answer. That's just helping me get my answer. Okay. Okay, now I want to answer my question. I want to find out when that polynomial is greater than 0. So I'm looking for all the areas where I'm positive. Okay, so I'm thinking this is a solution, this is a solution, okay, because I've marked them as positives. Do I want to use brackets or parentheses for those solutions? Parentheses, because if I go to my 0, then I'm equal to 0, and I want to be greater than 0. So I'm going to have a parentheses, and a parentheses there. Okay, all of those zeros are where I would equal 0, and I don't want that. This will help me write out my interval notation then. Okay, from -1 to 1, I'm positive. Non-inclusive, don't include -1 or 1, because then you're equal to 0, and that's not what you want. In union with 3 to positive infinity. Don't include 3, because 3 makes the function equal 0, because we've listed it as a 0. Now, this was my work. There's a lot of stuff going on up there. Draw a nice answer on a number line. Parenthesis, parenthesis, shade in between, parenthesis, shade to the right. Final answer. I have interval notation and I have a nice number line without too much stuff on it. Yep. Questions I can answer. When you're doing your homework assignment, I would encourage you, try some of those examples where you test in the intervals with the function notation. Try some examples where you use multiplicity to determine if it actually crosses at that intercept. And then also maybe check some of your work with your graphing calculator. Graph that polynomial and see if those are really the sections where it's above the x-axis or below the x-axis. Okay. Next up, I'm not going to give you as much time as I did for the first one, but I'm going to ask you to have a short discussion with your groups again, doing a rational function. So if I give you f of x equals x minus 5 over x plus 1, when is f of x greater than 0? Could you write that in interval notation again? And also, what ended up being the key numbers that you used to describe that? So here's a chance where to kind of formulate your ideas about that graph. You might actually want to graph it in the calculator. You might actually want to graph it on Desmos, one of those things, so that you can see the graph. Okay, so have a quick discussion. We'll come together and then we'll do an example with rational inequalities. Okay, so I've drawn an example of what you've probably seen on your graphing calculator or on Desmos. And the ideas that you should be talking about with your small groups is like, where are the sections where it's greater than 0? Okay, and if I were to highlight, I'm going to use my red marker. If I were to highlight all the places where my graph was greater than 0, this entire branch is greater than 0 because it sits above the horizontal asymptote that's at y equals 1. And so it's trapped there. It's never going to cross that asymptote, and it's going to be greater than 0 the whole time. Okay. When I look at the other branch on the right side of my vertical asymptote, I notice that there are sections where, like right next to the vertical asymptote, I'm coming up from negative infinity. So I'm negative in all of those locations until I hit my x-intercept at 5, and then beyond that x-intercept, I'm positive again. So does anybody have an interval notation they gave for that? What does that look like? Jacob?
Parentheses, negative infinity, -1, parentheses, union with 5, parentheses, infinity.
Yeah. Okay. Important here is that you're not going to include -1 because do you even have a graph at -1? No, so you've got to kind of keep in mind when you're doing the rational ones, what if you have a vertical asymptote, don't use brackets because you don't have a graph there. And then on this one, because we want to be greater than 0, we're going to exclude 5. If that's at greater than or equal to 0, then we would use a bracket for 5. Okay. What ended up being the key numbers in this example?
0
-1 and 5, which represent what in a rational function? The vertical asymptote and also the, no, it's not the horizontal asymptote. The horizontal asymptote is that one.
X-intercept.
The x-intercept, which we would call the x-intercept another 0, right? Okay. So when we do rational inequalities, the key numbers will be your zeros and your vertical asymptotes. Same rule applies. One side should equal 0 before you begin. So make one side equal 0 first. Key numbers are your zeros and your vertical asymptotes. The bullet points right underneath that is not new information. You know this from section 2.6. You were quizzed over it yesterday. To find the x-intercepts or 0, set your numerator equal to 0. To find the vertical asymptote, set your denominator equal to 0. So you're going to do that to find the key numbers in a rational inequality. Okay. You're going to test your intervals. At this point, we could use the same method we did last time, plugging numbers in for x and then seeing what we get out for y or f of x. Pay attention at that vertical asymptote. Mark it as a vertical asymptote in your work so that you know that it's not actually equaling 0 there like it does when it's an x-intercept. So you got to pay attention to like what key number is a vertical asymptote, what key number is actually 0. And then write your answer again in interval notation and sketch a graph using parentheses and brackets. If you do good work in between, the answer for interval notation and the graph is super quick and easy. If you've done good work to decide where your areas are positive and negative and when they're equal to 0. So we're going to do one example of a rational function, and I picked one that's not equal to 0 to begin with because you have to be careful with this if you're working with rational functions. I'll post them online later. We've got 3x minus 5 over x minus 3 is less than or equal to 1. And so we have to follow that same rule that we did for polynomials. We really don't want to work with it and talk about vertical asymptotes or x-intercepts until it's set equal to 0. So we'll have to subtract 1 from both sides. So I get something like 3x minus 5 over x minus 3 minus 1 is less than or equal to 0. Okay. But another issue is now presented to us. When we did section 2.6, we never had stuff that was added or subtracted on the back of the rational function. So what you need to do is you need to combine those two by getting common denominators so that you have one rational function, one fraction numerator over a denominator. So this is really like 1 over 1. What's a good common denominator? X minus 3, right? So we're going to multiply that by x minus 3 on the top and the bottom. That's the well-chosen one. X over 3 or x minus 3 over x minus 3 is equal to 1. So you have 3x minus 5 over x minus 3 minus x minus 3 over x minus 3, which to me I still read as minus 1 because something over itself is equal to 1. Don't forget now when you actually do subtraction, you're subtracting x, you're also subtracting negative 3, which is going to turn it into a plus 3. So you keep your denominator of x minus 3 now that you have common denominators. And in the numerator, 3x minus x is 2x. Negative 5 minus negative 3 is negative 2. Are we okay with that? If it's plus, it's not a super huge deal, but whenever you're subtracting, you'd have to distribute the negative. Okay. And we want to know when that's less than or equal to 0. Can I clarify anything?
Why is the denominator x minus 3?
Because the original fraction had an x minus 3 denominator. I was subtracting 1, so a good common denominator between 1 and x minus 3 is x minus 3. When you add 1/4 and 1/4, you keep the denominator the same. Okay? Okay, so now we want to go into our key numbers. Key numbers are going to be our zeros and vertical asymptotes. Zeros are x-intercepts. So set your numerator equal to 0. You're going to come up with an x-intercept at 1. So at 1, it's actually equal to 0. And on my work, I can say, here's 1. It equals 0 because it's an x-intercept. Find my vertical asymptotes at my denominator equal to 0. My vertical asymptote is at 3. There's no graph there because it's a vertical asymptote. So that's what I'm saying, like, be careful with your vertical asymptotes and your zeros. Remember that at that vertical asymptote, you should really have a parenthesis because it's not going to equal 0 ever there. Now test some numbers. So I might choose in the middle here 2. Okay, I'm going to evaluate f of 2. You're going to your new function to evaluate. So 2 times 2 is 4, minus 2 is 2, and then 2 minus 3 is negative 1. So I now know this whole section is negative. I can test some other numbers, like maybe I'll test 10 over here. F of 10 would be 20 minus 2 over 10 minus 3. I can tell that's going to be positive. A nice one to check over here is 0. F of 0 is going to be the ratio of the constants, so negative 2 over negative 3, which is really a positive. And so I've decided all the places where I broke up my graph with my key numbers. Now I've just got to go back in and decide what section am I looking for. I want it to be less than or equal to 0. Positive won't work. Will 1 work? Yeah, so I'll use a bracket at 1 because it's equal to 0. I want all this section in between. Will 3 work? No, there is no graph. And then beyond 3, I'm positive, so I don't want it. So when I write my answer in interval notation, I would say from 1 to 3. 1 is inclusive, 3 is exclusive. And then I'll graph it, 1, 3. I'll use a bracket at 1, a parentheses at 3, and shade in between. And so most of my work is already done if I do good work for the key numbers and the positive and the interval, positive and negative intervals. Great day.